Hello, everyone, and welcome. My name is Edina McAllister, and I'm part of the ASIS team. And we are so glad you could join us today for the webinar called AI Empowered Metadata Research and Information Analysis in Uncertain Environments. Throughout this presentation, feel free to type your questions into the Q&A box at any time. Please note that this session is being recorded and the recording will be made available on the ASIS website after the event. Now I am pleased to hand things over to your moderator who will introduce our in-STEAM presenter.
Hi, good morning. I am Gemma Bueno de la Fuente from Spain. I am the moderator of this session, and I want to introduce you also to Luan, the professor that is working or presenting this webinar. She comes from the Center of Studies of Information Resources from the Wuhan University. Wuhan, everybody know. Also, she's at the School of Information Management at the University of Wuhan. I hope everybody's interested in this topic. We have a lot of people coming in, and I really have reviewed it, and it's really, really powerful. So if you have any doubts, if you have any comments, please, as Edina proposed, use the chat or preferably the Q&A that you have below. So that's the time to Luan to present, and we really want to thank her for her presentation.
Thank Gemma for your introduction, and thank ASIS and DCMI for organizing this webinar. So I'm Luan from Wuhan University. It's my pleasure to present our recent studies on AI-empowered metadata research and information analysis in uncertain environment. In the recent years, we have faced many uncertain challenges, such as extreme weather, food shortage, weak economic growth, etc. Uncertainty is a phenomenon caused by incomplete or asymmetric information. As we know, Claude L. Shannon, the founder of information theory, indicated that the information transmitted through communication can reduce the receiver's uncertainty about something. Information science is a discipline about how to reduce uncertainty by providing information. The uncertain environment mainly includes uncertain data environment, uncertain semantic environment, and uncertain demand environment. As we know, information needs to be organized such as by metadata and analyzed to extract knowledge to better reduce uncertainty. Metadata can reduce uncertainty by providing structured descriptions of data, making it easier to classify, retrieve, and analyze information efficiently. In the uncertain environments, the ability to quickly gather, organize, and interpret metadata helps decision makers access relevant information in real time. AI empowerment enables dynamic, fine-grained, and semantic metadata research, such as automating the collection, classification, and analysis of various metadata. Here, I summarized our recent studies about AI-empowered metadata research in the uncertain environments in the 5 aspects. First, about intelligent metadata generation and enhancement. In this field, there are 3 types of research. First, about automatic extraction and annotation. Using natural language processing, computer vision, and other technologies, entities, attributes, relationships, events, and so forth are automatically identified and extracted from unstructured or semi-structured data to form structured metadata. Second, missing value prediction and completion. Using techniques such as knowledge graph embedding and graph neural networks based on existing data patterns, missing metadata information can be predicted and completed. Third, quality assessment and repair. Through AI methods such as pattern recognition and anomaly detection, we can automatically identify errors, inconsistencies, or redundancies in metadata and provide repair recommendations. Here, I would like to share our recent study about classification and severity assessment of disaster losses based on multimodal information in social media. As we know, social media provide abundant information. Here, we try to extract textual semantic features from microblog posts on Xinlang Weibo. It is the most popular microblogging platform in China, similar to X. The purpose is to capture real-time and specific descriptions of disasters from the public. And we can use the BERT model to generate metadata. They are a high-dimensional vector containing contextual semantic information about disaster losses in posts. Second, we can extract disaster background features from the government announcements. The purpose is to provide authoritative and structured disaster background to reduce information uncertainty. We can use the named entity recognition and BERT. First, we use NER to extract key entities from the announcements, and then input structured text into BERT to generate feature vectors. The generated metadata includes a vector representing the official disaster background, which provides important contextual constraints for disaster loss classification. Third, we can also extract image features from the images uploaded to the social media platform by users. The purpose is to provide visual evidence such as collapsed houses and road waterlogging. We can use VGG16 convolutional neural network to generate metadata such as a high-dimensional vector that encodes visual patterns and key object information in an image. The extracted three types of feature vectors are concatenated into a longer joined feature vector, which is then fed into a deep neural network for deep fusion. The fused unified feature vector is fed into a softmax classification layer, which outputs 5 fine-grained disaster loss labels. In this study, a fine-grained multimodal information-based disaster losses classification model, we call it MIDLC model, is proposed to identify the different types of disaster losses from massive social media data. These 5 types of tags are a carefully designed metadata system. So here, Table 1 shows the description of disaster loss types. There are casualties, houses and buildings collapse, municipal infrastructure damage, public service facilities damage, and impact on production and daily activities. Then we want to assess the severity of the disaster loss information. So Table 2 shows the severity assessment system of disaster loss based on social media. The criteria layer includes event information characteristics, and it also contains some basic indicators. These are the metadata of events. And there's also information dissemination strengths. They are the metadata of information. And official responses and user emotional volatility, they are the metadata of people. About the datasets, we selected 3 different disastrous events, including the Henan rainstorm in 2021, Typhoon Lakima in 2019 and Luding earthquake in 2022. After pre-processing, we obtained a total of 88,000 textual entries and 211,000 corresponding images. Table 3 shows the statistics of disaster event datasets. And Table 4 shows the sample distribution of 3 disaster events. Here we divide the datasets into training set and a test set. Let us see the performance of the MIDLC model. Table 5 shows the classification performance of the MIDLC model based on different learning rates and mini batches. And here we can see some numbers in bold. That means this is the best performance on different public events. And Table 6 shows the benchmark experiments results. Here we can see our proposed MIDLC model, that is multimodal information-based disaster loss classification model. Here, their precision, recall, and F1 score values are the highest. Higher than the baseline models, they only consider the image features or only consider textual features, or some of baselines also consider multimodal data. However, our proposed model has the highest performance. Finally, we can assess the severity of disaster loss. Here we can see this is the total severity, and we can see for each event, we can calculate the total severity according to their performance in the cyberspace. And here, different color bar shows the different types of disaster loss, such as casualties represented by orange. This is the highest in the Luding earthquake event. So this is our first study. Next, we are going to talk about semantic understanding and association discovery. In this field, there are also 3 aspects of research. The first is about entity linking and disambiguation. In uncertain text, we need to determine which specific entity a word or phrase points to. Second, cross-source, cross-domain, cross-language metadata alignment and mapping. Using methods such as representation learning and transfer learning, we can automatically discover and match semantic equivalence or correlation relationships between metadata from different sources, domains, or languages. The third aspect is about context-aware semantic richness, combining specific scenarios of data generation or usage. We can automatically add contextual tags, emotional tags, timeliness tags, and so forth to metadata to enhance its semantic dimension. Here, I would like to share one of our early studies about research on knowledge graph alignment model based on deep learning. As we know, the core components of a knowledge graph are entities, relationships, and attributes, which are essentially highly structured semantic metadata. Here, Figure 1 shows a graphical illustration of knowledge graph alignments. Here, M. Bancroft is a character. It's in DBpedia. However, in the Wikidata, it has a different name without the underline. And here in another 2 knowledge graph, MED and BBK, actually 珊瑚显镜 and 复方珊瑚姜丁水杨酸, actually they are the same object. However, they have different names in 2 knowledge graphs. So that's why we need entity alignment. This study focuses on entity alignment, which refers to identifying entities in different knowledge graphs that point to the same real-world object. This belongs to the matching, linking, and fusion of metadata. The research object is to align and integrate metadata, addressing the redundancy and inconsistency issues between multiple source knowledge graphs with the aim of integrating them into a high-quality, unified knowledge graph. The main contributions of our work are as follows. First, we propose a novel knowledge graph alignment model. We call it KGA, based on deep representation learning. Second, our findings shed light on negative sampling with respect to knowledge graph alignment. We propose a novel negative sampling method, that is, transformation negative sampling, that enhances the effectiveness of linear transformation of space compared with traditional triple negative sampling. Third, we examine the key influencing factors of KGA. This study aims to address the research question of domain knowledge alignment from the perspective of knowledge graphs. Specifically, how do we find the same entity and relation between different knowledge graphs? Suppose there are two knowledge graphs, namely KG1 and KG2. Suppose AE is a set of aligned entities. The goal is to infer the new alignments in E1 and E2. Please look at this figure. It is a graphical representation of the KGA architecture. KGA includes a knowledge graph embedding module and a vector space alignment module. The input of the model includes knowledge graph triples from two different sources, that is KG1 and KG2, and a small portion of seed pairs. The knowledge graph embedding module aims to train the entity vector on different knowledge graphs separately. The vector space alignment module aims to employ the aligned entity pairs to learn the transformation matrix from the source vector space to the target vector space. First, let's look at the knowledge graph embedding module. Two knowledge graphs of different sources are utilized to learn the embeddings of the entities and relations. First, initial vectors of the entities and relations are generated by a normal distribution based on a given vector space dimension. The KGA model employs the negative samples to generate the corresponding negative triples. As we know, if we train the datasets, we both need positive samples and negative samples. And positive samples, they are the true relations. However, the negative samples, they are false. They do not exist, but we create to train the data. The Trans-E model is utilized to train the corresponding k-dimensional vectors of the entities. We refer the above process as triple negative sampling. Triple negative sampling refers to the fact that for a particular triple in a knowledge graph, HRT, its corresponding negative triple, that is H prime, R prime, and T prime, is generated according to a certain strategy, which is jointly utilized to train the embeddings of entities and relations. In the negative sampling, to make the embeddings more distinguishable, different negative sampling strategies are investigated. The KGA model deploys 4 different negative sampling strategies. First, random tail entity replacement. For a triple head, relation, tail, an entity from the entity set E is randomly selected as the tail entity of the negative triple. Second, random head or tail entity replacement. For a triple HRT, an entity from the entity set E is randomly selected as the head or tail of the negative triple. Third, random relation and tail replacement. For a triple HRT, a relationship is randomly selected from the relation set R as a negative instance triple. At the same time, An entity from the entity set E is randomly selected as the tail entity of the negative triple. 4. Weighted tail sampling. As the frequencies of the entities appearing in a knowledge graph are different, the frequency is considered while replacing the tail entities. So in the vector space alignment module, a small number of aligned entities are employed to learn a transformation matrix M, through which the entities from different sources are projected into the same target space for comparison. Negative sampling techniques are used to generate negative entity pairs. Actually, they are false, they don't exist, but we create the negative samples so that we can train the data set and adds them to the training set as a supplement to the positive entity pairs. They are true pairs. They really exist. Given an aligned entity pair, an entity from the entity set E is randomly selected to replace E2. We refer to the process as transformation negative sampling, as the transformation matrix M is trained jointly by the aligned and unaligned entity pairs. About the baselines, to validate the quality of the proposed model, we conducted a comparative study with the state-of-the-art methods including M-trans-E, IP-trans-E, and REA. All the models employ the structured information of knowledge graphs. About the evaluation metrics, we employ two typical evaluation indicators. They are hits at top K and mean reciprocal rank. Hits at K indicates the proportion of correct entities appearing in the top K entities for each instance. MRR counts the average of the reciprocal of this ranking. Here we can see the equation. A better alignment quality is indicated by a higher hits at K value and an MRR value. About the data sets, three groups of data sets, that is, the heterogeneous knowledge graphs, the cross-lingual knowledge graphs, and the domain-specific knowledge graphs are employed in our study. For heterogeneous data sets, three subsets of mainstream knowledge graph, that is DBpedia, Wikidata, and Yago, are sampled. For cross-lingual datasets, three subsets of DBpedia in the language of English, French, and German are sampled. We also add two more benchmarks. They are domain-dependent, that is MED-BKK, it's a medical knowledge graph, and HPO, MPO, it's about drug. To further investigate the performance on domain-specific benchmark datasets. Table 1 shows the number of entities, relations, and triples for each dataset. Let's see the results of heterogeneous knowledge graph alignment. Table 2 shows the overall performance on the heterogeneous datasets. These are the baselines, and we can see that our proposed model KGA, here we can see the numbers in bold are all the performance of KGA. That means the evaluation results of heterogeneous knowledge graph alignment demonstrate that the proposed KGA model performs better than those of the baseline model. Next, let's look at the results of cross-lingual knowledge graph alignment. Table 3 shows the overall performance on the cross-lingual datasets. Here we can see this is English, this is German, this is English and French. And also we can see that the numbers in bold all belongs to KGA. That means the results of the KGA model are better than those of the baselines. Finally, let's look at the results of domain-specific knowledge graph alignment. Table 4 shows the results. Again, we can see that this is MedBBK, it's a medical knowledge graph, and HPO, MPO, it's about human drug knowledge graph. And again, we can see that the numbers in bold, they all belong to the performance of KGA. So for both two domain-specific data sets, the KGA model greatly outperformed the baselines. So this is our second study. Next, I'm going to talk about context-aware semantic richness. Here, I would like to share our study about a knowledge graph completion model, integrating entity description and network structure. As we know, knowledge graph is a structured and semantic form of metadata organization. But the knowledge graph is facing the challenges of incompleteness. Misinformation is common in knowledge base. For instance, the nationality information of about 70% of people in free base is missing. If the knowledge base does not contain the triple Jeff Bezos graduated from Princeton University, a Q&A system may not answer questions such as which university did Jeff Bezos graduate from? Thus, this study focuses on the task of completing knowledge graphs, which involves automatically predicting and completing missing triplets, essentially enhancing the integrity, consistency, and richness of metadata. Here, we propose a novel entity description augmented knowledge graph completion model and investigate the following research questions. First, compared with the traditional knowledge graph completion models and those that incorporate external information, does the proposed model have a better effect on the knowledge graph completion task? Second, what are the key influencing factors for the knowledge graph completion model integrating entity description and network structure? Third, what is the applicability of the knowledge graph completion model in different scenarios? In what aspects are the advantages of the proposed model mainly reflected? Here we can see the EDA KGC model consists of three modules. First is a representation initialization module and a deep interaction module. The third is an inference module. The representation initialization module takes the entity description as the input and encodes it using the pre-trained language model, that is BERT. The second module is deep interaction module. It first uses the relationship representation to obtain the convolution kernel corresponding to the relationship. Then the convolutional kernel is employed to extract the features concerning the entity representation vector and the interaction between the entity and the relationship. The deep interaction feature vector between the entity and the relationship is acquired through feature aggregation. The third module is reasoning module. It performs a matrix operation between the deep interaction feature vector and entity representation matrix to obtain the probability distribution of tail entities. About the data sets, here we conduct intensive experiments on 4 data sets. And this is Table 1 shows the statistical description of the experimental data sets. And here we can see the number of training data set and valid test data sets. About the evaluation metrics, there are 4 evaluation indicators, namely hits at 1, hits at 3, hits at 10, and MRR. So just now I introduced their meaning. About the baselines, we compare the performance with 2 types of model. They are the structure-based models and the text-enhanced models on the 4 data sets. The structure-based models include trans-E, rotate-E, dismount, etc. The text-enhanced models includes DKRL, etc., a lot of baselines. Table 3 shows the comparison results. Here we can see the proposed EDA KGC model achieves the best results concerning all the 4 indicators on the FB15K datasets. So next, I'm going to talk about dynamic evolution and adaptive management. In this field, there are 2 aspects of research. First is about metadata evolution modeling. We can utilize techniques such as time series analysis and dynamic knowledge graphs to track and analyze the patterns of metadata entities, relationships, and semantics over time. Second, self-description and adaptive metadata. Research on intelligent systems that can automatically adjust, expand, or recommend new metadata schemes based on environmental changes, such as the addition of new data sources or changes in user needs. Here, I would like to share our recent study about archetypes of influential users in social question answering sites. In this study, we extract features from user behavior data and content data. These features are used as inputs for clustering and regression analysis, essentially constructing and utilizing behavioral metadata and content metadata. First, we need to identify the influential users. The data was drawn from Zhihu. It is one of the most popular social query answer platforms in China. Content related to the COVID-19 pandemic was chosen. An initial corpus of 2.3 million postings comprising answers and comments was collected. Table 2 shows the dimensions of user influence. The dimensions include attention, popularity, competence, and activity. So these indicators, actually, they are the metadata of users. Table 3 shows the features used to determine influential user archetype. Basically, the features include behavior and content, and the indicators include answers, promptness, interaction, emotion, and quality. The 5 indicators of influential users in each phase were extracted separately, which were then used to classify the archetypes of influential users using the Gaussian mixture model. Next, we are going to analyze the archetype change. Each influential user would have 2 archetypes, an initial one X and a subsequent one Y. To observe any archetype change, the concepts of support and confidence of association rules were used, as they provide an effectively quantifiable way to measure the strength of relationships. Support of the rule is the proportion of times the given archetype pair XY appears together in the dataset. Confidence of the rule is the ratio of times the given archetype pair XY appears in the dataset to the times the archetype X appears in the initial phase in the dataset. To investigate how user feedback influences archetype change, the multinomial logistic regression model was used, given that archetype change, which was the dependent variable, is nominally scaled. Table 4 shows the operational of variables. Here we can see dependent variable is archetype change. The independent variables include several groups. The first group are central root related variables, such as quality, comprehensiveness, relevance, and consistency. The peripheral root related variables include volume, timeliness, commenter diversity, and control variables include social support, information self-disclosure, identity verification. Next, the GMM algorithm was applied to identify influential user archetypes based on the extracted 5 indicators over the 2 phases. The number of archetypes was selected as 3. So figure 1 shows the classification results. There are 3 clusters. First is touch and go influential users. Second is proactive influential users. The third is super influential users. So table 5 shows the support and confidence of archetype change. And we can see that touch and go and proactive are the most common archetypes into which influential users from other archetypes change. Next, I'm going to talk about intelligent retrieval, recommendation, and decision support. Here we have 3 types of research. First is about semantic retrieval and question answering. Based on deep semantic understanding, we can achieve precise information retrieval and question answering that goes beyond keyword matching and understands user intent, even if the query request is vague or uncertain. Second, metadata-based intelligent recommendation. Reinforcement learning, graph neural networks, and so forth are used to recommend relevant data, services, or analysis paths based on user historical behavior and dynamic metadata features. Third, uncertainty reasoning. When there is uncertainty in the metadata itself, probability graph models, Bayesian networks, and so forth are used for reasoning to provide confidence support for decision-making. Here, I would like to share our recent study about a benchmark for evaluating crisis information generation capabilities in large language models. This study aims to establish benchmarks to comprehensively evaluate the performance of large language models in crisis information generation in scenarios like natural disasters, accidents, and public health events. So here, actually, we want to find which large language model is good at generate response to the public events. First, we need to generate the civil dataset. Table 1 shows the subjects of civil. It includes several types of public events. About the data collection and pre-processing, the primary sources of the raw data are post-disaster recovery plans and accident investigation reports publicly released by emergency management departments. Data related to cybersecurity events comes from typical case collections issued by cybersecurity companies like QAX. About the dataset generation method, we utilized the generative capabilities of large language models to build an evaluation dataset, providing abundant test resources for assessing large language model performance in specific crisis information needs. Figure 1 shows the overview of civil generation methods. Here we can see the time, location, disaster situation. Actually, they are the structured metadata about the public events. The dataset construction process follows a systematic pipeline approach. First, about event information extraction. Pre-processed documents are put into GPT 4.0, which automatically extracts key event information from the documents. The information includes, but not limited to, occurrence time, disaster type, and economic losses. They are the inputs. Second, targeted question generation. Based on the response measures, policy, protection, suggestions, and other information in the input document, GPT 4.0 randomly generates a series of crisis-related questions. They are the instruction. 3. Prompt construction. GPT 4.0 is used to combine input and instruction to form a complete dataset for assessing the crisis information generation capability of large language models. 4th, manual review. The automatically generated prompts undergo rigorous manual review to ensure clarity, fluency, and high relevance to the crisis information tasks. These are the process metadata. The dataset includes 4 major categories of crisis types, and the civil contains a total of 4,800 evaluation questions. Table 3 shows the description of the models. Here we can see the metadata of the models, such as developer, size, access, and source. About the evaluation method, this study uses a combined evaluation method of manual scoring and machine scoring. About the manual scoring, we established evaluation indicators for crisis information generation capabilities of large language models, including content quality, expression quality, feasibility, and effectiveness. These are the metadata to define quality, and we ask 3 PhD students with relevant experience in the field of crisis information were invited as evaluators. This study further explores the possibility of machine scoring. We selected GPT 4.0 and Claude 3.5 Sonnet as machine scoring experts. The optimal model score is chosen to replace manual scoring to save labor costs. Let's see the results. Comparison between manual scoring and machine scoring. Correlation tests were conducted between manual scoring and Claude 3.5 Sonnet and GPT 4.0 scoring, respectively. Finally, GPT 4.0 was selected as the main tool for evaluating crisis information generation capabilities of large language models. Let's see the results. Here we can see GPT 4.0 has the longest bar, the highest score. That means it has the best performance on the whole. And the figure on the right shows the score of large language models in different types of crisis. And figure 3 shows the score of large language models' crisis information generation capabilities in segmented scenarios. So all kinds of public events. So finally, I will briefly introduce governance and trustworthy assurance. There are 3 types of research. First is interpretability and traceability. We can develop technology that can explain how AI generates or recommends specific metadata, ensuring transparency and trustworthy of the process. At the same time, the generation, circulation, and change history of metadata are recorded. Second, deviation, detection, and fairness. We need to identify and mitigate potential biases in metadata and the AI models that generate metadata, ensuring fairness in data services. Third, privacy-oriented metadata design. Technologies such as federated learning and differential privacy are utilized to generate and utilize valuable metadata while protecting the privacy of raw data. So this is my presentation. Thank you.
Thank you, Luan. It has been very interesting and very powerful, your presentation, with a lot of information, maybe hard to process very quickly. And we have some questions and comments in the chat and the Q&A. I could pass it to you. I don't know if you can read it, but first we have one about the question of fake images. If the model addresses the use of fake images related to the social media, like that. That's the first question we have. I have 6. This is the first.
Okay. So let me see. Can I see the questions?
Yeah, it has been answered. So you have it in the like one slide questions, then answer question, and then unregarded questions.
So
I have
I see
answered just to say
there
thanks.
there is a question in the chat bot. So about the archetypes of influential users, what are the touch and go, proactive, and super influential user? So yes, just now I briefly introduced how we cluster the influential users into 3 types. So I will briefly explain what does each type mean. So for the first cluster, this archetype is characterized by offering fast answers without any interaction with users. Compared to their counterparts, these influential users tend to leave the community immediately after finishing answers. Yet their prompt and moderate quality responses make them a reliable information source which users can turn to. So that's why we call it touch and go influential users. The second cluster is labeled as actually it is characterized by a rapid and active behavior in giving high quality answers. They are the vanguard of the community, enthusiastic about sharing their knowledge and experience with others who have questions in the first instance. So that's why we call it proactive influential users. For the third cluster, this archetype is characterized by interacting actively with the users and providing exceptionally high-quality answers. They are the pillars of the community and generously dedicate their time, energy to build relationships with community members and contributing their expertise. So that's why we call it a super influential users. So
okay, there are more questions. Oh, I don't know if you can see it, but I can share it to you if the
yes, I can see. So there is a
okay.
question about
Yeah,
how
we have the
to
question from Lily Day about the use of fake images.
the fake images. So
Yeah.
actually, we have studies about fake images, but this study is not shared by me today. I have another. So I can briefly introduce later. So if you are interested. So actually, we have conducted a research about fake news detection. So we collect posts and images from social media platforms, and we both processed text and images. I remember that we processed the images by VGG19 models so that we can fuse the multimodal information so that we can detect fake news, including the fake images. But today I didn't reproduce this study. So I remember I published on IPM, information processing and management. So if you are interested, you can read about it. So I would like to answer the question how to maintain robustness of multimodal disaster classification models. So robustness is a very important issue. So just now I mentioned our proposed study about multimodal disaster loss classification model. We call it MIDOC model. So the robustness of the model is mainly guaranteed through 3 levels. The first is about the data preprocessing, and the second is model architecture design, and the third aspect is comprehensive experimental verification. First, about data preprocessing and enhancement, we need to filter high-quality data. We need to remove posts unrelated to the public events through keyword matching and semantic similarity analysis, and filter low-resolution or damaged images using preset thresholds to ensure the basic quality of the input data. Second, sometimes we lose some model. For example, some text is missing. Then we can fill neutral placeholder images for posts with only images, maintain consistent input structure, and avoid model collapse due to model missing. And another case is the image is imbalance. For the case of one post with multiple images, an average pooling strategy is adopted to fuse multiple image features into a unified representation. Third, about the text-image pairing. Ultimately, we retain 1-to-1 ratio paired data samples to provide a stable foundation for subsequent feature-level fusion. And next, we also introduce structured background information. We extract authoritative and structured disaster background information from the government announcements. They could provide external knowledge anchors for the model. So the first aspect to ensure robustness is data preprocessing and enhancement. The second aspect is model architecture and fusion strategy. So actually, we adopt a hierarchical feature extraction. For the text features, we use BERT model to extract deep semantic features to better understand the context and cope with colloquial and concise social media texts. For the image features, we extract visual features using the VGG16 model, which has a simple structure and strong feature extraction ability. And for the background features, the BERT is also used to encode structured background information, provide stable event context. And then we fuse different models of features, combine the above 3 types of feature vectors into a long vector by using the deep neural networks for deep long linear fusion and introducing attention mechanisms to dynamically adjust the weights of different model features. And the third aspect is comprehensive experimental verification. Actually, just now I showed the comparison results, and we can see that the proposed model MIDOC outperforms the baselines. So that's my answer to the how to maintain the robustness of the method. Okay, let me see the query and answer.
Yeah, we have the question from Lily, you already answered, and from Jennifer Letcher, and then Lilian Ebovo, and Nina.
Yes, just now I explained my studies about fake images. Actually, it's a study about fake news, both including fake news, text news, and fake images. In this study, we compare the inconsistency between the text and images, because if we transform the images into vectors, then you can find that sometimes the text is about something, however, the image is about another thing. or in different year in another event, in another topic. So that is the clue to find the fake images.
Then it was about another question about social media, if it was predictive of reality or whatever.
Here I can see a query about wondering if social media is predictive of reality. Was your social media checked against true data created after the event with official data about the people, infrastructure, and structure slots, or did you not have access to the official data? So actually, so far, all of our studies, the data source come from open data source. So I can only access, for example, the social media platforms in different countries and different languages, Chinese, English, and some others. Social media, yes, sometimes the social media can be used to predict the reality. Actually, I conducted some research about predict the influence of social media posts. Sometimes we can see that some people post a message on social media and suddenly it becomes a very hot topic and a lot of people retweet, forward, comment, and like, and click on likes. And some other posts, when they put on the social media platform, no one see it. It's just a silence. So I established a model to predict what kind of post could be influential post in future. So in that study, I create a feature system, including what is the feature of the author of the post, what is the feature about the time, so when is the post posted, and I find it very interesting finding. So some posts, for example, they put in the midnight, and some of the posts are put in the morning or afternoon, or some of them are generated on the holidays or during the weekdays. Then all these features will influence the potential influence of that post. And also the influence of the post is related to the topic. So some specific topics, they tend to attract attention of other people. So yes, so we collect data from the social media. And just now I explained, if we want to train a model, we need positive samples and negative samples. For example, just now I talk about my model to predict the influence of a social media post. We label, for example, if the number of forwarding, comments, and likes, if the total sum exceeding a threshold, it is labeled as high influence posts. And if a post without any attention, that is low influence post. So these are true data. And then we can, using this data sets, to train a model to predict the future of these posts. So I wonder if I answered this question. I also see a question about, I want to know, is the metadata research method empowered by AI universal? So that is a very big question. So actually, when I say uncertain environment, it is a very broad concept, right? The universality of AI-empowered metadata research does not mean that a trained model can be directly applied in another field, but rather than its core methodology, technical framework, and solution ideas can serve as a powerful toolbox that can be customized and transformed to solve some similar problems in different fields. The study I I shared today, including the MIDOC, KGA, EDA, KGC model, user influence analysis, although in different scenarios, they have successfully abstracted a universal AI-empowered metadata research paradigm. So we need to transform the main problems into metadata generation, alignment, enrichment, or mining problems. So I can give you some examples of domain migration. For example, in the medical field, we can input medical images and doctors' oral reports. The model can automatically generate a structured metadata report containing tumor location, size, and nature. And in the financial field, we can scan the corporate annual reports, press releases, and financial charts. The model can automatically extract and classify metadata such as changes in financial indicators, risk events, and management signals. And in another field, for example, education field, the model can analyze videos, slides, and discussion forum posts of online courses. The model can automatically generate metadata annotated with knowledge units, paragraphs, difficult questions, and classroom interaction hotspots. So
Okay.
I wonder if I answered this question.
I think you did it very well, and I'm afraid we are over time. There is, in my time, 4:03. There is
Okay,
one more
thank you.
question. People saying thank you very much. So I think people need to, at least me, I have to process all the information you presented. It's quite complex and rich, and I really appreciate and thank you, Luan, for your presentation. And let's see if we can replicate something that you did it. Okay.
Thank you, Hema, for your moderation, and thank you all the audience for your attention. So it's my pleasure to see you all.
On behalf of ASIS, I would like to extend our heartfelt thanks to our presenter and moderator for presenting this webinar. I sincerely thank you for joining us today, and this concludes our session. Have a great day.
Have a nice day.
Have a nice day.
Bye bye.
Bye bye.